We looked at the idea of Euler trails and Euler tours in the video on the bridges of Königsberg. What we want to do now is take a look at this topic in a little bit more precise detail. So first of all, we should remember that a walk is called closed if it starts and ends in the same place. So a walk that goes from U to V of some length is closed if U equals V. So you start and end at the same vertex. And a trail is a walk with no repeated edges. Now, just because it has no repeated edges doesn't mean it doesn't repeat vertices. It's possible that a trail repeats vertices. So a trail is not the same thing as a path. A path does not repeat vertices. Now, what makes a trail an Euler trail is if it hits every vertex exactly once. So an Euler trail, it's a trail that visits every edge once. So we were looking for an Euler trail in the graph that represented the bridges of Königsberg, and the point of that video was to show that such a trail does not exist in that graph. Now, there's another word which is Euler tour, and that is an Euler trail that is also closed. So Euler tour, it's an Euler trail that is closed. So in other words, it visits every edge exactly once, and it also starts and ends at the same vertex. So that's what makes it an Euler tour. And if a graph has an Euler tour, it is called Eulerian. So now we have a more precise definition for what we mean by Euler trails and Euler tours. And maybe the first big theorem that we should take a look at is something that's not too difficult to show. So I'll write it here as a theorem. I'll just scroll down so we still have the definition of Euler tour. And let's call this theorem. So a connected graph G is Eulerian if and only if, and just for mathematical reasons we sometimes write IFF for if and only if, and that can also be replaced by this symbol. So if and only if every vertex of G has even degree. Now, if you remember from the video about the bridges of Königsberg, you'll remember that we had a result that said if we had an Euler trail, then the number of vertices of odd degree had to be either 0 or 2, exactly 0 or exactly 2 vertices of odd degree. But that was for the existence of an Euler trail. If you want to have an Euler tour, which is what we mean when we say Eulerian, then that tour is actually a closed trail, and then we require every vertex to have even degree. And not only that, but if every vertex has even degree, then there will be an Euler tour of the graph. So this theorem was actually done in part by Euler himself. That was from 1736, but the full proof of this theorem was really given by the following mathematician. I'm probably pronouncing it wrong, Herke, and that was in 1873. So quite a long time passed before a full proof was given, but Euler did have the basic ideas for this. So let's take a look at a proof. Now the first part is quite straightforward because if we suppose that the graph is Eulerian, it's easy to show that every vertex will have an even degree. So that's this direction. We'll say suppose G is a connected Eulerian graph. Connected Eulerian graph. So that means that it has an Euler tour. So let's say let W, which goes from a vertex U and it goes back to the same vertex because it's closed, be an Euler tour. Now let V be any vertex. For now, let's just take V to not be U, but any vertex of the graph G. So V is a vertex of G that occurs K times in the Euler tour. K times in W. Now, just point out to yourself that V will definitely occur in W. Every vertex will occur in the Euler tour because the graph is connected and every edge gets used up in the Euler tour. So we have a vertex that occurs K times in the tour. Well, then that means that every time an edge arrives at the vertex V, so this vertex V occurs K times, but for every time we have it occur, we have to arrive and then leave from the vertex. So we arrive on one edge and we leave on another edge. We arrive on one edge, we leave on another edge. So this means that the degree of the vertex is equal to 2 times k, because for every time you arrive at the vertex, you have to leave on a different edge. So we've already seen this sort of argument done in the video on the bridges of Königsberg, and hopefully we can all agree that the degree of the vertex will be even. But what about vertex U? Why is it still having even degree? Well, the reason is because if you consider vertex U and then there's some trail, actually a tour, W, any time that W comes across vertex U, it will have to enter and then exit from that vertex. So again, you're going to have this same sort of argument having an even number. However, we started and we ended here. So there's the start. Maybe I'll do the start in one color. So this is like the start. And also in another color, we end. And every other time, it's just a regular vertex that has an entrance and an exit. And maybe it's not used other than the start and the end, but it could be. So any intermediate visit to vertex U will have to use up an even number of edges, and it also starts and ends. So it should also be clear that also the degree of U is even. So that means that all of the vertices of the graph have even degree. So that just proves the first part. That proves that if the graph is Eulerian, i.e. it has an Euler tour, then every vertex has even degree. Now what we want to do is show that if every vertex has even degree, the graph is going to be Eulerian. So let's suppose that we have a graph where every vertex has even degree. So we're going this direction now. So let's let G be a non-trivial. Now the reason why I'm writing non-trivial is because if G is the trivial graph on one vertex, then there is a trivial Euler tour which is not taking any edges, and you're already done. So let G be a non-trivial connected graph. Connected graph whose vertices are all have even degree. Whose vertices all have even degree. Okay, so what we want to do is to show that this is in fact an Eulerian graph. Now the way we do this is we're going to actually have to be a little bit subtle here. We're going to do something where we take a longest trail in the graph. Now when we take a longest trail, it doesn't necessarily mean that it's the only longest trail. There could be other long trails of the same length, but for this particular longest trail, you cannot extend it to a longer trail. So what we do is we start off by doing that. We take a longest trail. So let W be a longest trail in the graph. And I'm going to actually say what W is. I'm just going to give it some notation. So let's say that we are going to start with vertex V0 and then use up an edge E1 to get to vertex V1, and then another edge E2 to get to vertex V2, and we keep going. So we're going from vertex all the way through like this, through all these edges, and continue, and we get to E. Let's just say this is L minus 1 to vertex L minus 1, and then EL to VL. Okay, so basically W is a longest trail from V0 to VL, and in fact we can see that there are exactly L of these edges, so it has length L. Of course we don't know what L is, we're just calling it the length of a longest trail. Okay, so it is a longest trail, and then now what we have to do is take a look at the fact that VL should actually be the same as V0. And why is this? Well, the reason is because W, this walk, cannot be extended to a longer walk. So that means that when we have reached vertex VL, all of the edges that exit out of vertex VL have to be used up in the walk W. Otherwise, we could just simply extend it. And because if VL was to occur k times throughout this walk, then if we were to just end at VL, then it would have an odd degree, but we know it has an even degree. So since it has an even degree, and since we've used up all of the edges that come out of it, it follows that VL has to be equal to V0. So let's write that down. Since all neighbors, so all edges incident with VL are used in the walk, and VL has even degree, then we must have VL equal to V0. Okay, so what we know now is that W is in fact closed. But let me just be extra careful here, and I just want to make sure that it's clear. All edges incident with VL are used in W. The reason for that is that otherwise W could be extended to a longer trail. And the reason here that if VL was not V0, so this part here, is because if VL is not V0, and VL will occur some number of times in the walk, so let's say VL occurs k times in the walk in W, so I should just say in W, then the degree of VL would be equal to, well, every time W hits the vertex VL, we arrive and then we exit, and that happens for k minus 1 of the times that it's visited, but then it ends at VL, and this is a problem because this is going to turn out to be an odd number, and that's what happens if these two vertices are not identified. So that's why we know that these two vertices are in fact identified. So what we have right now is that W is actually a closed trail. Thus, W is a closed trail. Now our aim is to in fact show that W is going to be an Euler tour. So right now we know it's a closed trail, but what we want to show is that it in fact is an Euler tour. And so what we can do is we can say, well, if it's not an Euler tour, then hopefully we'll be able to come to a contradiction. So let's suppose that W is not an Euler tour, right? We're hoping that it is an Euler tour, so let's suppose that it's not, and hopefully we will come to a contradiction. Well, now since the graph is connected, since G is connected, then we know we have not hit all of the edges of the graph because W is not an Euler tour, so there are still some edges out there. But since it's connected, there's definitely going to be an edge that touches on W. So here we have our walk W, and so we're walking along and we get to a vertex VI, and we continue along in our walk. Now VI is going to be incident with some other vertex out here, U. So basically there is an edge that has not been used up. So actually I'll just use a different color right here to indicate this edge existing. So since G is connected, there's going to be an edge. There is an edge, and let's call it F, and it's going to touch on the walk by a vertex, but the edge itself is not going to be in the walk. So let's just say that it hits a vertex VI, but then some other vertex, U, which was not contained in the walk. So this is an edge of the graph, but it's not an edge of the walk. So hopefully that's pretty clear. But now what we can do is actually find a longer walk, and here's how we do it. We can start here at U, and then we can move down that edge, traverse through the walk, and now we arrive at where? Well, VL. However, we know that VL is identified with, in fact, V0. These are the same vertex. So really what you could think of is this wraps around here, and that just is V0. If you continue along this walk, you will end up at V0. And you continue to follow the trail W, and you end at vertex VI. And this is in fact a longer walk, a longer trail. So let's just write that down. Then, if you were to use up the edge F, and then the edge EI plus 1, and you continue to use W until you get to the last edge EL. Now EL took us to vertex VL, but vertex VL is V0, so then you continue to use the next edge, and the next edge of the walk we called E1. So you use E1 and you keep going until you get to EI. So essentially this whole piece right here, from here to here, this is W. But if you tack on F at the beginning here, now you have a longer walk. So this is a longer walk. Whoops. And so that is in fact a contradiction, because there can be no longer trail than the one we already have, W. We took W to be a longest trail. So we just found a longer one. That's a contradiction. So it's a contradiction of our assumption that the walk was not an Euler tour. So this walk here, which was in fact a closed trail, it is indeed an Euler tour, because if we suppose that it's not, we come to this contradiction.